What do you got?
Could you do number 6?
6. Oh, of course. This one looks so difficult, and it's not, but it's a little tricky because if you don't see the triangles, then it's not much. Doesn't seem like you have enough information to do it, right? All right. So if I want the height of this liquid, how far is that piece? That's 22. Why?
Because, like, the radius.
It's also, yep, it's a radius of the sphere, right? Cool with that? So that's one part of the height. If I can figure out that piece, then we know the height of the water. Everybody agree with that? So I need to build a triangle that involves the side x. The triangle that you should build is that triangle. How long is that orange side that I just drew in? 22. Why is that 22? It's also a radius of the sphere. And then from there, Elaine, I think you're probably good, right?
Yes.
So again, that's the tricky part, is realizing that anything you draw from the center of the sphere to the surface is a radius. So there's like a whole mess of radii in here that'll be really helpful to you. It's about realizing that you can draw those in, and they're all just 22s. Does that feel good? Again, if you don't notice that, it feels like there's not enough information. But once you see it, it's like, oh, that's easy. But it's like one of those tricks you just got to see first, right? What else do you guys have? Okay, that's fine. We don't need to do, if you don't have any more questions right now, we can always circle back as you go a little bit further into the problem set and run into more stuff you're unfamiliar with. We'll continue on then into section 9.3. So again, as a reminder, I have the PowerPoints built out for this chapter 9 just because there's so much drawing involved. It was easier to do it this way than have to write everything down. I think do you remember, did I load all these PowerPoints in on My Notre Dame?
Yeah.
Okay. I thought I did the first day that we talked, but sometimes you just need to double check, right? All right. So last time, we did a bunch of vocab, reviewed a bunch of formulas from our geometry or previous math courses, and we talked about how to find some of these side lengths inside of these three-dimensional figures, right? Today we're going to continue on. We're going to talk now about finding angle measures within these three-dimensional figures. Do you suppose this is going to be decidedly different than the side length piece? No, the approach is going to be almost identical. You're going to build yourself some calculation triangles and use SOHCAHTOA to find your angle measures. It's fairly straightforward. So again, calculation triangles. The thing that's a little bit tricky is that if we have a side or a line that intersects a plane, like the side of a figure, doesn't matter where that's happening, the angle between the line and the side of the figure is that angle between any line in the figure and that angle. So you're just going to pick a segment that's like coplanar to this segment that's coming in, intersecting the plane. So in those things, like, it's hard to explain in words if you just kind of like close your eyes and visualize what's happening. It's like, oh yeah, sure. You know, if you have a stick and I'm holding it at an angle against the floor, it's like, what angle does it make with the floor? It's like, well, you just, you know, it's like, oh yeah, of course. That's kind of what this picture is supposed to look like. So again, common calculation triangles. We've talked about calculation triangles can be kind of sneaky because they may not look like right triangles on the flat piece of paper, but they actually are. So let's go and hit some examples here. So on most of these angle examples, you're going to have to do some side length stuff also in order to get enough information to do your angle piece. So this one, we've broken it down into 4 parts. We're going to find the length of EB, the length of DB, the length of DE, and then the angle that DE makes with the base of the prism, which is this angle that we've drawn in here in pink. Okay. So let's start by finding the height for EB. What's the calculation triangle I'm going to use for that? I'm going to use AEB. Notice that I have the 21-degree angle there, and I know that AB and DC have to be the same length. So that's my calculation triangle I'm going to use. What am I going to use to find EB? Tangent, good, because relative to the 21-degree angle, EB is opposite and 15 is adjacent. So I just say tan is equal to EB over 15, solve for EB, and I get 576. As you're doing this, what mode should our calculator be in? Degree. Whole chapter should be in degree mode. So if you haven't fired up your calculator in a minute to check, might be a good idea before you get too deep into this to make sure you're in degree mode so you don't sit there banging your head against the desk going, why am I not getting the right answer? This should work. And it's because you're in the wrong mode, and that's always embarrassing. All right, let's go and find the length for DB now. So that's this segment here that's on the bottom of this wedge. The calculation triangle we will use here should be DBC. I agree. Very good. So DBC is a right angle. We know DC is 15, and we know BC and AD have to be the same. So that's the bottom face. So finding angle DB, we can just use Pythagorean theorem. Yeah. Oops, wrong way. And that's pretty easy, right? Again, the hard part is seeing the calculation triangle that you need. In general, after you've accomplished that, the arithmetic we need to get to the answer is usually quite simple, right? It's a Pythagorean theorem or a SOHCAHTOA, things that we're comfortable doing since, geometry days. The difficulty here is like seeing it in 3 dimensions. Okay. Next thing we're looking for is the segment DE now. Yeah, so if I use the triangle DBE, we just solve for DB and we solve for EB. So Pythagorean theorem with our 2 previous answers is going to get us DE. That's exactly right. And then the last piece, if we're looking for that angle BDE, that one in pink, we have all three sides of the triangle, so this should be easy. You have a lot of flexibility as to what you want to do to find that angle. I'm going to use the previous two answers to write a tan inverse of opposite over adjacent. So I get it like 11.84. Which should feel pretty okay, right? Feel so far so good? No big deal? Okay. All right. So let's say we have a cylindrical drum. Contains a stick that fits the diagonal exactly. If the radius of the drum is 5.8 centimeters and the height is 15.8 centimeters, calculate the length of the stick and the angle that the stick makes with the side of the drum. So here's our picture. Let's do part A first and calculate the length of the stick. So the calculation triangle here that we would use is ABC. We know that BC is clearly 15.8. What is AC then? Yeah, it's going to be 5.8 doubled, so 11.6. And then we can just use the Pythagorean theorem to get that length for AB. Does that feel hopefully pretty easy, right? This one, there wasn't a lot going on. It's pretty easy to see the triangle you need. Part B then asks the angle that the stick makes with the side of the drum. So which angle are we looking for here? So you need three vertices, right? To name an angle. Because if you just say angle A, I don't know if you're talking about this angle or that angle. So BAC would be the angle formed between the stick and the bottom of the drum. This is asking for the side. So I want ABC, right? This angle here, which I know from geometry will also be the same as this angle over here, which is the one I think Rita was asking to find, right? Why are those going to be the same angles? They're alternate interior angles, yeah. That the radius or the diameter of the top should be parallel to the diameter of the bottom. So these are alternate interior angles. So with that, I can use tan inverse, right? Notice I didn't use the hypotenuse here. Why not use the hypotenuse? Why use these numbers? More accurate because they are not rounded. The hypotenuse we would have had to round. Not that it would make much of a difference. You would still, to rounding to 2 decimal points, probably are going to be fine. If you're trying to, like you have a planet the size of a cylindrical drum, now maybe that makes a difference between your missile being like 2 miles off when you try to shoot your missile or whatever. Like it's a matter of scale, right? For a drum that's a couple 15 centimeters high, it probably doesn't matter. So far, so good. Okay. Look at this fancy clip art here. A rescue helicopter is hovering 156 meters above the sea. It is dark, and the helicopter is shining a light down onto the surface of the sea. The diameter of the cone formed by the beam of light is 140 meters. What is the angle at the apex of the cone? So the angle at the apex is LMO, What's the problem with using the triangle LMO?
It's not right.
It's not a right triangle. So what are we going to do?
Use like one of the triangles.
Yeah, we're going to use one of the triangles and take that answer and double it. Why? How do I know that that's actually, that little pink angle is half of LMO?
Because the height is
But why? Why would that happen? Does it happen for all triangles? It doesn't happen for all triangles. It does for this triangle because it's a special kind of triangle. It's an isosceles triangle, yes. So if you have an isosceles triangle, then that altitude is going to also be an angle bisector. But it has to be isosceles. And we know that like a right cone is isosceles, right? Okay. So there's my shimmy-madoo. Where'd the 70 come from? Half of the diameter, very good. And so now we just tan inverse opposite over adjacent and multiply by 2. No problem. What do you guys think? Is it like basically the same thing as the previous section, right? Like, oh no, I have to use an inverse trig function. This is so hard. Yeah, but not really, right? It's like, it's a big, no big deal section, okay? And guess what? That was 9.3. Yeah. Let's go ahead and finish up 9.4 here. So 9.4, we're going to be calculating volumes and surface areas. So info dump has some common volume and surface area formulas. Patow! So the volumes we're probably relatively familiar with, like cuboid, length times width times height. Pyramid, 1/3 area of the base times the height. Cone, 1/3 pi r squared h, since the area of the base is a circle. Sphere, 4/3 pi r cubed. Hemisphere is just half of a sphere. Right prism, area of base times the height. Cylinder, pi r squared times the height. So again, area of the base is a circle times the height. So those ones are probably relatively familiar. The surface areas, what in the heck is a surface area? You basically just like cutting the figure so it lies out flat. We call that a net. And then we're just calculating the area of each of the faces. So for a cuboid, a box, it's going to have 6 sides, right? The ends are the same area. The top and bottom are the same area. And the front and the back are the same area. So you have 2 times height times width plus length times height plus length times width. So those are like those 3 different kinds of faces, and there's 2 of each of them. If I have a right pyramid and my base is a quadrilateral, well, I'm going to have the base, that's the quadrilateral, and then I have 4 triangles, right, that I have to calculate the area for. Now, if the base is a square, what are those triangles all going to be? The same. They're going to be the same triangle. If the base is a rectangle, they're going to be, yeah, 2 pairs of them will be the same. What if it's like a pentagon? How many triangles are you going to have? 5, right? 1 for each side of the base. You're going to have a triangle for. And if it's a regular pentagon, all the triangles will be the same. If it's not, they could all be different. Ooh, hopefully not. I'm going to run into a problem like that. That sounds like a lot of work. So the cone, same idea. You have the area of the base is the circle, pi r squared. And then the cone part, if you cut along and fold it open, that's going to be pi r l, where L is that slant height. So like the distance along an edge. Sphere, the surface area is 4 pi r squared, which is a surprising result that the surface area of a sphere is 4 circles. Like that's weird. At least that I always think that's weird, but hey, okay. A hemisphere is going to either be half of the surface area of a sphere if it's like an egg where there's no bottom to it, like if it's just like a cup. If it does have a bottom to it, like instead of, you know, like slicing through a basketball where there's no insides, you slice through like a jawbreaker where there's stuff in the middle, then there is a bottom to it. So you have one more circle. That's why it's going from 2 pi r squared to 3 pi r squared. Does that make sense to you guys when I say that? You get what I'm saying? Between like a ball versus like, you know, like something that's got insides to it. If I have a right prism, again, we have 2 bases. If the bases are quadrilateral, that means there's going to be 4 other rectangular faces. If the base was a pentagon, how many rectangular faces would we have? 5. If it was a hexagon, we'd have 6, etc., etc., etc. A cylinder is 2 pi r squared h. That's assumed that's the part, just like the sides of the cylinder. If you want to count the bases also, like the circle on top and bottom, then you have the plus 2 pi r squared. So again, just kind of depends on whether you're counting, you know, if it's like a pipe where it doesn't have ends to it, or if it's like a Pringles can or something. Everybody cool? Yes, go ahead.
Like a test or quiz, we have to like know all these like 5 by 3 or
Oh no. Oh no. No. Don't waste your time doing that. And really, in all reality, the surface area formulas, if you just like unfold the figure, yeah, just like the area of each of these little composite figures. So it's like it looks complicated, but it's like one of those, like, I don't even use the formulas. I just kind of like unfold it. It seems easier to me. All right. So let's do a couple of example problems. So let's say we have 3 tennis balls are packed in a cylindrical container. Anybody play tennis in here? You know what this looks like then, right? Should be an expert on this. So the balls are just touching the sides, top and bottom, when they're all stacked in the container. The diameter of a tennis ball is 6.7 centimeters. We're going to figure out the internal height of the cylinder, the diameter for the cylinder, the volume of the container, and then we're going to say the curved surface of the cylinder is going to be made out of plastic, but the top and bottoms are going to be metal. So we're going to need to figure out how much area of plastic we need versus how much area of metal we need. So it's a complicated setup, or at least an involved problem where there's a lot of steps to do. Okay. Let's start here with the internal height and the diameter for the container. So here's my cylinder. There's my tennis ball with a diameter of 6.7. What's the height of the container going to be?
like 6.7 times 3.
Yep, because you have 3 tennis balls stacked up in there. Each of them has a diameter of 6.7. And then what's the diameter for the container going to be? 6.7, because we say the tennis balls are just touching the top, sides, and bottom, so there's no wiggle room in there. So that's pretty easy. Again, if you play tennis and used to looking at this thing, it's probably more obvious than if you're like, I don't know what the heck you're talking about. I only play racquetball, and only 2 balls come in a racquetball container. This makes no sense to me. This is a joke, because it's clear. It's just like it's the same problem. All right, so we have that. So the volume of the container then is going to be area of the base times the height. So the base is a circle, so that's pi r squared, and then the height So the radius here was half of the diameter. So that's the 33.5. And the height we said was 20.1. So that gives us 708.66 cubic centimeters. So far, so good. It then says that the curved surface of the container is going to be made out of plastic, and then the top and bottom side of metal. So the area of the sides was that pi r 8 or 2 pi r h. So it's the circumference of the circle times the height, because when you unwrap this, you have a rectangle where the base of the rectangle is the perimeter or the circumference of the circle, and the height of the rectangle is the same as the height of the cylinder. If you think about it in your head, if you unfold that, I know that's tricky sometimes. Okay. And then if I want the area of metal used, that's just going to be 2 pi r squared, right? For one circle on top and one circle on the bottom. So there's that. Feel okay here? All right. The base of a prism is a regular hexagon with the sides 3.5. That's 3.5 centimeters for the sides of the hexagon. And the length for the prism is 19 centimeters. We're going to find the volume of the prism and then the surface area of the prism. Okay with that? So here's my picture. To calculate the volume of this, the volume is just area of the base times the height. So the trick here is going to be calculating the area of this regular hexagon. Right? That's going to be the sticking point, since we have the height right away. How do I calculate the area of a regular hexagon like that? Well, you might have remembered from geometry there was an area formula for a regular figure. I don't remember what that is, though. What I'm going to do is I'm just going to take my hexagon and divide it up into 6 identical isosceles triangles. Everybody's okay there? And then so I know that the base of that, or that hexagonal base, is just going to be 6 times the area of one of these triangles, right? Okay. Now, if I look up here, how many degrees are all of these angles going to make together? 360. And how many places have I split that 360 in? 6. So there's going to be 6 of these identical 60-degree angles up here, right? 360 divided by 6 is going to be 60 degrees, all up here. Everybody agree? All right, so let's just look at this triangle here that has a 60-degree angle at its apex. We said this was an isosceles triangle, right? What do you know about the base angles of an isosceles triangle? They're congruent. So I have 60 degrees here, which means there's 120 degrees left for these two angles. And they're the same measure, so they have to be 60 degrees also, right? So I don't have just an isosceles triangle here. I actually have equilateral. Which is nice, because how am I going to calculate the area for this now? You could do 1/2 base times height. You're going to have to solve for the height. That would be fine. What else could you use, though? it's a non-right triangle, you could do 1/2 AB sine C, which that's what I would use, since I know all of the side lengths are 3.5 and all the angles are 60. 1/2 AB sine C is 1/2 3.5 squared times sine of 60 degrees. Boy, that feels a lot easier than trying to, like, you can drop in your perpendicular bisector, and that's going to split the 3.5 into, 1.75 and 1.75, and then you can use, like the Pythagorean theorem, or you could use the SOHCAHTOA or whatever to find the height of the triangle. That's okay. But this is what I would use. So one of those triangles is 5.3 centimeters squared. So 6 of them is the base of the hexagon. And the height for my prism then is the other piece that I have is 19. So that gives me 604.7 for the volume. Everybody okay with that? Here's a nice thing I'll tell you. These bases for your prism, if it's not a triangle or quadrilateral, it's going to be a regular figure, so you'll be able to do this, like, divide it up into a bunch of isosceles triangles thing, same thing that we've done here. Just FYI. So you'll see this again, I think, in the homework. All right, now we need the surface area, right? So we have 2 hexagonal faces, but we already know the areas for those, right? We did that already in the previous part. Right? We know the base area for the base of the hexagon is this 31.8 number. So we already have that. And then we have 6 of these rectangular faces. Those rectangles are 19 by 3.5. So I have that base for the hexagon already. My rectangle is 19 times 3.5. So I have 2 times that 6 times 5.3 number, and then 6 times that 19 times 3.5 number. They give us 462.65 centimeters squared. Yeah, go ahead.
For like that hexagon part, they use the 5.3.
Well, that was the area for one of the triangles, right? The hexagon was 6 times the area of one of those triangles.
Oh.
So I just kept the same.
Okay.
I just kept the same work rather than using that 31 number from before, because it was just kind of like stashed inside the calculation. I think I just probably copied and pasted this line
Oh, that makes sense.
when I was building this out, because it was less it was less work, like going and moving around all these little things.
Yeah.
Does that feel okay, everybody? All right.
Oh, yeah.
I got one more, I think. So we have a lampshade is going to be made from a cone of glass with a glass hemisphere as its base. The slant height of the cone is 29 centimeters, and the diameter of the hemisphere is 11 centimeters. We're going to calculate the surface area for the lamp, and then the volume for the lamp shade. So what's going on here is, like, this cone is sitting on top of that hemisphere, right? That's going to be what the lamp looks like. So the surfaces are just going to be the part of the cone without the circle, and then the hemisphere without the top. Everybody agree with that? because the cone's going to just sit down on top, so all that stuff would be on the inside technically, the two circles. So I have the surface area for the outside, or the not everything except for the base of the cone is pi r L, and a hemisphere with no top to it is 2 pi r squared. So we know that the radius is going to be 5.5. How did I get that? Half of 11. And I know the radius for this hemisphere has to be the same as the radius for the cone because it's going to set right down on top of it. And then L we know is the slant height, which we're given as 29 plus 2 pi r, and it's the same r, 5.5 squared. So that gives us 691.15 centimeters squared. Feel okay there? Next up, we want the volume for the lampshade. Let's see, lampshade. Why am I doing the hemisphere? I don't care. Well, the volume of the lamp. Forget the shade there then. There we go. Volume of the lamp. Scoopers. I got a bunch of edits to make. Anyways, so that's going to be the volume of the cone plus the volume of the hemisphere, right? The volume for a cone is 1/3 pi r squared h, and the volume for the hemisphere is 2/3 pi r cubed. Well, the only thing we're missing here, we have the radius, that's 5.5, half of 11, but we don't have the height of the cone. So we're going to use a calculation triangle here and the Pythagorean theorem to find that value for h. So I get about 2847. And then I can just plug in and add them together. And I get 1,250.44 cubic centimeters. Hey, what do you say? We're done. Yeah, again, this chapter should be not too bad. In general, if you are uncomfortable like visualizing something in 3 dimensions, it can be a little bit tricky for that, but should be okay. At this point, you guys can now do 8 through the end, whatever that comes out to, 32. The good news is we're done for today, so you have 40 minutes to make some progress on that, which is pretty righteous. And the X day tomorrow, I'm just going to call this the review day and let you just work on your stuffs. Hannah?
Is 1 through 7 do you want to Sunday, or is like the entire song?
Just 1 through 7. The next problem set wouldn't be due until like after you've come back from vacation. Well, I haven't put the review guide in yet either, have I? Let's take a look here. Right, did I not? Haven't done that yet? Let's drop that in. Yeah.
So I wasn't here on the first day, and I'm just like so confused on like how to find like the main triangle to look at. Like I don't know.
Okay. One quick second.
Okay, no worries.
Just real quick here, I just dropped in the review stuff. If you look at the last page of the review as to Rita's question, do I have to memorize all this junk? This is all the junk that you're given as, as your equation sheet for this test, which is, I think, pretty sufficient, right? Anything that's not listed here, you're responsible for, but at least that narrows down a big chunk of it, right? As far as test day goes, what would you guys rather do? Do you want to have the test like the day we come back? Or do you want to like start the next chapter for a day and then do the test the following?
Do we come back? B-Day Monday?
No, because it's an X on Friday, so it'll be Tuesday. Your test day would be Tuesday if you want to do it the first class back. We'll talk about it again tomorrow.
Okay.
Deal? Then we don't have to make this decision now. But that's your option. So think on what you think is going to be nicer. Mr. Kulik doesn't care about due dates. All right, let me pause this recording.